So, there exists V phi u comma v where u is fixed is a SAT instance because it is trying to find this satisfying assignment V. And since we assume that SAT has poly-size circuits, circuit family CM, so why not pick CM where M is the size of the instance and give this u and phi to CM, and now it will correctly answer. It will answer 1 if there is a satisfying assignment, and now let us try to find this assignment. So, CM can be used to in fact find a satisfying assignment V. So, how is that? Basically fix V. So, first you have checked that CM u phi is 1, right, this you have checked. So, then what you can do in the second step is fix V1 to 1 or V1 to 0. So, now if CM u comma phi V1 equal to 0, if this is 1, then we have found V1. Else, if this is false, then it means that you have to set V1 to 1. One of them has to work, right? Both cannot fail. If both fail, then it means that CM u phi is unsatisfiable, but that step 1 has ensured it is satisfiable. So, next what you can do is you go with u phi and whatever V1 you found out. So, V1 we will just use what we got, and V2 we can now play the same game. So, whatever V1 was fixed in the step 2, so V1 was defined here to be 0 or 1, and now V2 we will try to fix. So, if V2 equal to 0 works, then else you set V2 to be 1. So, now V1, V2 both are fixed and you keep going. And now you can output the values V1, V2 and V. We did not say how many variables there are in V. Suppose it was N. Can output that. Okay, so this is a satisfying assignment that you have found. So, this V is a satisfying assignment. Of phi u comma V. So, you see using CM you can actually compute a satisfying assignment. So, let us call this thing we just did, we can convert it into a circuit and call it CM prime. So, convert this algorithm into a circuit, call it CM prime. Okay, so CM prime basically outputs the satisfying assignment. So, CM prime when given phi given, we are writing it as u comma phi, is equal to a satisfying assignment V. Assignment V of phi u comma V. Okay, so it outputs an n-bit string. That's the circuit CM prime. So this means that now we can write, if there exists a V if this is true, there exists a V there exists this satisfying assignment V, then indeed we can just plug in, instead of V we can plug in this CM prime. And vice versa, right. So, if there is a satisfying assignment, then CM prime u comma phi is that, it works, and if CM prime u comma phi cannot give an output that satisfies phi u comma dot, then it only means that there is no satisfying assignment. So, now you can rewrite psi, right, that was for all there exists phi, for all u there exists V phi u comma V, that psi we can rewrite. So, thus psi is so psi was what? Psi was for all u there exists V phi u comma V is equivalent to that there exists a circuit CM prime such that whatever u string u is given, phi u comma CM prime with phi comma u as input accepts. Okay. So, this is the beauty of the circuit. What it has done is it has flipped for all there exists to there exist for all, because now this there exists is acting on circuits which are not too big, right. CM prime is only poly-sized, let me mention that. So, CM prime is a poly-sized circuit which you are looking for. If that exists, then no matter what u is, for all u, phi u comma this output of CM prime will force phi to accept. So, psi is equivalent to this, and that means that we have put pi 2 sat in sigma 2. Which means that pi 2 is sigma 2, which means that the polynomial hierarchy collapses to sigma 2, right. So, that finishes the proof of Karp-Lipton theorem that if SAT has Boolean circuits, then the polynomial hierarchy collapses. And there is a nice corollary to this. Let us also do that. So, suppose that something even more drastic happens. Exponential time algorithms, they all have poly-size circuits. So, all the exponential time solvable problems can be solved by Turing machines with advice in polynomial time. Then what will happen? Then the same thing happens. So, actually x becomes equal to sigma 2. This proof is similar to what we did. So, the idea here is simulate or check every step of the Turing machine. Of the exponential time Turing machine. Okay, it's any problem L in X will have an exponential time Turing machine. Look at its steps. The steps are easy to check, and basically there will be a circuit that can do that of the exponential time Turing machine by using the circuit. If there is a circuit that exists for X, then every step we will check by that circuit. Thus simulating so exponential time Turing machine, let us call it, give it a name M, thus simulating M by sigma 2. Okay, let's see the implementation of this. How is this done? So, suppose L is in EXP and it has a poly-size circuit. L has first exponential time Turing machine, M. Assume that it has a circuit also. Poly n size circuit Cn, this circuit family Cn having polynomial size, computes the jth bit of the ith configuration of M running on X. Okay, so this is implied by L in P/poly. We have Cn from, we have Cn as L is in P/poly. Okay, that basically, if you want the jth bit of the ith configuration, any bit of the ith configuration of M running on X, clearly that is computable in exponential time. And since we have assumed X pin P/poly, sorry, I should say X pin P/poly. since we have assumed that exp is in P slash poly, this circuit will exist, okay, which computes some any bit you want, your favorite bit from the ith configuration. And now we can check each and every step of m of x using quantifiers. Let us do that. So observe that x is in L if and only if for every configuration I and for every bit position j, this what did we use, Cn, right. So Cn on x comma I comma j to Cn x comma I plus 1 j, this is a valid step of m. Right. So, what we have written here is something something obvious. What this for all I comma j is checking is every possible configuration to the next happened in the correct way, following the finite control of Turing machine M given input x of length n. Okay, this is easy to check. This is in polynomial time. This is in polynomial time because you just have to look at the look at the finite control of M and what that dictates. Like look at the transition function basically. From there it will follow. So this can be checked from easy to check from the transition function delta m. Right. So using the transition function, it can be easily checked whether this is a valid step. We have broken the computation into steps and we have applied for all operators. So then m must be accepting x. So x is in L if and only if m of x is 1, if and only if this happens. Now all you have to do is, I mean the circuit you don't know, so that we can say using existential quantifier. So this means that x is in L if and only if there exists a circuit C n says that for all I, for all j, this check passes through. Okay, that's all. So if x is a yes string, there will exist a circuit such that for all the configurations which are exponentially many and for all the bits in the configurations which is also exponentially many, if you do a check, then the check matches. Okay, and since the check matches, it matches, that is what m would be doing identically. It's a identical, I mean it's a thorough check of m of x computation, and hence it is equivalent to x being a yes string. So this means that L is in sigma 2, right. So exp is in sigma 2 then. and once x is in sigma 2, what happens? So, everything above sigma between x sigma 2 and x, they become equal. Sigma 2 then is equal to polynomial hierarchy, which is equal to p raised to sharp p, which is equal to then p space, and which is equal to x. Right. So, that was what we had claimed. So, if x has polynomial size circuits, then essentially these none of this do we believe, but it will happen. Okay, so, this is theoretical evidence that EXPs cannot have polynomial size circuits, but it is an open question. So, that is open, that X is not in P/poly. Okay, we conjecture that X is not in P/poly, but we do not know for sure, and obviously we also conjecture that NP is not in P/poly. Okay, so these are the famous conjectures, and we have shown theoretical evidence for them here. Okay, so what do we do next? Right, so Turing machines with advice, even they cannot solve SAT. Let us, and they are equivalent to polynomial size circuits. Let us give another interpretation of circuits, okay, third interpretation, if you will, and that is to do with parallel computation. So, Turing machine or algorithm is a is a sequential way of doing things. Of solving a problem. Why is it sequential? Because Turing machine or algorithm gives you after one step what comes next and what comes after that, and so on. There is no idea of solving many things at once. That is what you want in parallel computation. So, how do we model that properly? That is the question. So, what about parallel algorithms? Where do they live? Who models them? So, let us define some terms. What do we mean by parallel? So, a decision problem, or in fact it will not matter. So, any problem, functional as well, a problem L we say has an efficient parallel algorithm if on all the inputs so for all lengths and in that length all inputs, whether x is in L or not, or doing this, I mean given input x, solving the problem L, this L of x can be solved in polynomial in log n time, which is very fast, right? For on input of size bit size n, you want to solve a problem in poly log n time, which means you cannot even see the whole input. But what is parallel in this? So for parallel, we will actually say that the number of processors is many. So can be solved in poly log n time by a parallel computer that uses poly n processors. Okay, so this problem L, we will say it has efficient parallel algorithm if for all inputs of length n, as n is growing, you can solve the problem on this input in polynomial in polylog time and poly n processors. Okay, this is important. So when you talk about parallel computation, you actually want many processors, because one processor can do only one thing at a time, but many processors can do many things. And since you have poly n processors, they can look at different parts of the input. They can overall cover the whole input, and maybe together they can solve it much faster, and this poly log n is much faster. So you have to note that poly log n, which is much less than n. Okay, so in terms of the input size, the time is much smaller. So this is the advantage of parallel computation over sequential. Is there an interesting example which can be solved in parallel algorithm fast or parallel computer fast? Yeah, so show that for n bit integers x and y, x plus y can be computed in only log n time. If you use many processors. So by using order n processors. Right. So while it will take, I mean, if you do it just manually by one processor, you at least have to go through the length of x and y. So that will take order n time. By one processor. Right. So sequential algorithm will give you linear time, but parallel computer gives you exponentially lower than that, and this we will next time model via circuits.